thank you everyone for coming for our session. I'm Nikhil, and he's Luke. We'll be introducing ourselves and playing with the robots as well as figuring out, what we did to solve a simple yet complex problem of pathfinding. By introduction, I'm Nikhil Nanivadekar. I work at Goldman Sachs in Salt Lake City. I'm a vice president there. I joined Goldman in 2012. My academic background is I'm a robotics engineer. I have a master's in mechanical engineering from University of Utah, and I build robots as a passion. And one of my mentors is sitting out in the audience, who actually helped me build my first robot after joining Goldman. And we took it to Java 1 a couple of years ago, and it was a big hit. And from there onwards, the whole aspect of presenting a talk about robots started. I'll let Luke introduce himself, and he'll take it over.
Sure. So my name's Luke Torjussen. I'm Vice President at Goldman Sachs. I'm based in the New York office. My background was computer science. Not actually touched robots until very recently when Nikhil asked me to join him on this talk. So pretty excited to show how much I've been able to learn in a short space of time as well. So we've got a quick video we're going to show you. We're then going to talk through using Java as well as EV3's programmer app. So EV3 is one of the types of brick you can get on those Lego Mindstorms. That's what you can see at the front there. Nikhil's then going to talk through Dijkstra and the A-star algorithm as well, and then how he ended up implementing that on one of those Lego Mindstorms, where you've actually got some hardware constraints, so some resource constraints there. And then we actually have an interactive demo. We can talk about the compact profiles at the end, but I think the interactive demo is a bit more fun. So let's just jump across to this quick video. This is a video this is actually from EclipseCon last year. So last year at EclipseCon in Reston, Virginia, we had these robots doing, it's not moving on the screen. There we go, okay. So this robot is actually solving the classic Towers of Hanoi problem. If you will remember that problem, you have ideally have three sticks and three rings of different sizes. You need to move the three rings from the far right, in this case the bottom of the screen, up to the ring on the other end. But you can never put a bigger ring on top of a smaller one. So the way that this robot's actually working is it has the pulley, which is just a piece of thread, which is moving up and down, and an electromagnet. So we're actually engaging the magnet and disengaging the magnet when we want to release those rings. So actually worked quite nicely on the carpet. You sometimes have some traction problems, but this one worked quite nicely. So I can leave you to watch another minute of it, or we can just get on. So let's jump back into the slides here. Oh, it actually keeps playing, does it? Okay. Okay. Okay, so that was our quick video, show you what you can do. I'm also going to do another quick demo for you, actually live coding it. It's only about 15 lines of code. I actually did this for the very first time yesterday, actually on Sunday. We were at DevOps for Kids and actually had the kids building an elevator, which was pretty fun. Hopefully you enjoy it as much as the kids did. Quickly talking through the EV3 app, though. So EV3, as I mentioned, is the brick. It comes with a programmer app, so you can click and drag some components, which is great if you're not a programmer, especially for the kids wanting to get moving the robots around. It has the ability to plug in various sensors, as well as different movements, pick up, drop something. As soon as you want to start dealing with state or trying to predict where you might need to go based on some complex algorithm, this starts to fall down. So although it's great for kids getting started, if you want to do anything more advanced, you really need to jump into the code. So what you can do is there is a Java build called Lighthouse. And so what this really does is it's a collection of libraries you deploy on there with a ARM JVM runtime onto the brick, and allows you to control the motor, the sensors, and everything else. But your code looks like Java, you just have another library you're making use of. Also, one thing to point out is that better motor control. This is, I think in the EV3 app, you can kind of jump forward 10, but you can't do that inching forward just a little bit further to make sure I reach my object, which you can get that very, very fine-tuned control there using Lighthouse. So I kind of mentioned this, the first half of this slide, but once you've built your Java app, what you need to do is you need to get, obviously, your produced application onto the brick. So what you do for that is you jar it up, you SSH and copy the jar into a standard location, and then you can actually control it from the LCD screen on there. Luckily, Eclipse IDE has a plugin, so you click one button, it does all the magic for you. So that's what we'll make use of today. So before we do that, I'm actually going to just jump in and do some live coding. So we can see the elevator on this table in front of us. It is connected. There's a small man sitting or lying down in the elevator. He fell over. All we're going to do is make the motor that's attached go up and go back down on the push of a button. So as an elevator works, it only has 2 levels. So what we're going to do then, the first thing we need to do is we need to get hold of the motor. Conveniently, there is a function called motor, a class called motor with a constant called a. And I'm going to assign, oh my goodness, I got assign. It might be easier if you stand. If I stand here and code? Yeah. Oh yes, I can see much better now. Pulley motor. So here's my pulley motor. I'm then going to say, I'm going to do this in a loop because I might want to make it go up and down a number of times. And I'm going to just set up a quick loop. I'm going to ask for the press of a button. How do I do that? Well, there's a button class. And there is wait for any event, which returns back an int. And that int is the ID of the button that was pressed. So button pressed. I'm going to say if button pressed is button, and then there's a number of constants, so you have up, down, left, right, etc. So I'm going to say if it's up, there's an ID on the button here. If it's up, I'm going to say, oh, I missed a parenthesis at the end there, didn't I? So if it's here, I'm going to say pulley motor dot rotate, and after doing some calibration, it's about 2.5 turns, so it's 900 degrees. To turn it, I will do else if button pressed equals button down. Pulley motor rotate minus 900. And then just because I'd like to be able to stop the program at some point, I'm going to add one last thing here to just say break. So if I push any other button, break. OK, so you can see it's a pretty trivial amount of code. And if I hit, if I right-click, just as you would in any other Eclipse project, there's instead of run as a Java application, there's run as EV3 program. So I'm going to hit that. What that's now going to do is it's going to start jarring up and deploying it. So on the screen here, you can't see from there. Maybe the photographer here can see it saying, wait a second. And now it's ready. So obviously, the elevator is at the bottom right now. If I push up, up goes the elevator. And if I push down, no, it stopped. What did I do?
Oh, it just did an else. You need else if.
Else if, yes. That would explain it. But you get the idea. So buggy code is the cause of the issue here, not the robot itself.
This was pre-rehearsed, so.
Pre-rehearsed, yes, of course. I'll say if I hit the enter button, break. Okay. And I will go again, run it. Okay, so it's going to do the deploy again. Okay, so down we go. Up we go. And down we go again. Make sense? And if I hit the middle button, which is enter, it now goes back to the default LCD screen there. So that's very simple, quick live demo of how you can code up the Lego Mindstorms. Obviously, elevator is quite a simple problem. Nikhil's now going to talk through something slightly more complex. He's going to talk about pathfinding.
Oh, I do have to speak in the mic first. Thanks, Luke. One of the things which I wanted to quickly mention about the elevators is on Sunday, while DevOps for Kids was going, the kids actually built the elevators and programmed. They wrote a similar program. We made it slightly easier because they were kids, but they did do something similar. So it's interesting to see that, hey, you don't need to be an adult to play with robots. You can be a kid, or you can be an adult. There's like age no bar kind of thing, all right? So going back in the more complicated stuff, like that was very straightforward. But being a robotics engineer, one of the things which they taught me was motion planning or pathfinding. And one of the foundations of motion planning is the Dijkstra algorithm. And to quickly give you a brief of about what exactly Dijkstra's algorithm is it's the least cost path. It's the algorithm which will give you the least cost path. What that means is, consider that you want to find path from point A to point B. And this is a nice GIF which is available on Wikipedia. And the thing about Dijkstra is it's a knowledge-based algorithm. What that means is you need to know beforehand how your entire map looks like, how your entire graph looks like. You need to know beforehand which point connects to which other point, all right? You also need to know beforehand how much cost you have to pay to go from one point to the other point, all right? Now, like ours is a simple problem where we want to go from point A to point B, and there are like each of the connections has a cost. And Dijkstra being a knowledge-based algorithm, what that means is you can actually now investigate each and every node, which you do, because for you to find what is the least cost, you have to actually investigate each and every node. So you can see that from A or point 1, you can go to point 2, point 3, point 6. But the way the GIF works is it keeps on eliminating as and how it looks at the node. And it keeps on updating the cost that it is taking for it to go to that node. And at the end of it, the minimizing function is the cost, and you get the final cost. All right? Any questions so far? A star is an extension of the Dijkstra algorithm, where Dijkstra is the function, or the minimizing function is the cost. A star, you want to extend it by adding a heuristic to it. And you want to use that heuristic to basically direct the path towards the target, okay? And the heuristic can be anything. It can be distance, it can be time. Like the way I like to explain it to anyone is, consider Google Maps or any other GPS for that matter. Like you get generally 3 options. One is the shortest path, one is the ecological path, one is the fastest path. Now, depending on which path you want to choose, like if you want to go fastest, then time becomes your heuristic because you want to minimize the time. Here we are talking all about minimization, all right? If it is shortest, then you don't care about the time, you care about the distance. If it is ecological, then generally it is about, hey, how many traffic lights are there, how long will your speed be constant, is it going to be like a high-speed freeway, or it's going to be like 5 miles per hour or something like that. So the heuristic depends, and finding the heuristic is art more than a science. And just to quickly explain what the cost functions means, if you see Dijkstra, your function is C of n, where n is the node, to visit, and you want to minimize Fn. Similarly, A star is Fn of Cn plus Hn, where H is the heuristic, right? Any questions so far? No. So now going back to why we are here. We're here to explain how we got these tiny Lego mindstorms to actually solve a simple problem for a human, but more complex for a machine, of solving a maze. And I mean, when we were kids, we used to solve a maze as one of the exercises to go from the start to go to the end. And but when you are dealing with a system like robots, it becomes slightly more difficult because you have to program. You're the brains of that robot, right? What humans get instinctively, the robots don't necessarily get. Okay. Now going back to Dijkstra, again, it's a knowledge-based algorithm, so you need to have the whole graph in memory. The second thing is you need to have the weight or the cost that it takes to go from point 1 to point 2. And this is an arbitrary, like this was for experimental purposes, so the cost that I have taken is in order to go in the x direction, it takes one unit or one cost you have to pay to traverse one point. If you're traveling in the y direction, and again, it's absolute distance. We don't want to work with the negatives and all of those things. And whenever you are moving in y direction, it's twice the absolute distance, right? And the maze that we were trying to solve was this. So the star is the start, the checkered flag is the endpoint, and as you can see, there are two options. One is you can go to the right or you can go to the left. And depending on which one is cheaper, the algorithm will find it. So a few things which to note about the graph is it was easiest to actually get the RGB data out in order to process the whole graph instead of getting the whole adjacency matrix out. We use red color as traversable and blue color as obstacle. And the reason why these colors were chosen is it just looks better in the presentation. Because having a whole slide of dark blue color, it's slightly daunting to the eyes. We use that data to form an adjacency matrix of x and y coordinates. What that means is, does anybody know what an adjacency matrix is? So what an adjacency... Yeah, pretty much.
Okay, so you have, I guess, your list of, instead of the full matrix where you compare everything to everything else, you just, maybe you have you store the things that are filled. So if you have like a sparse matrix, you don't need to store all the zeros, you just store the one.
Exactly. So, but in a matrix, you actually end up, so consider that if you load up the whole graph, it will end up showing that point 1 can connect to point 2, 3, and 4, for example. All right. Then point 2 can connect to point 1, 3, and 6. All right. And that's pretty much is called as adjacency matrix. We use the adjacency matrix and the color data to get the nodes. Okay. And what that means is we'll see in the next slide. So before we do anything, we got to store it on the memory, and we use a mutable object int map for it. That's a different map than a JDK map. So like Luke mentioned before, Lihos is another Java runtime. So you can load up your third-party libraries. And Eclipse Collections, which was migrated to the Eclipse Foundation a couple of years ago, it actually has primitive collections. So an object int map has the key to be the object, which is our point, and int is the primitive int instead of an integer. That ends up saving quite a lot of memory. And what we do is we keep on creating this whole map of graph, like the whole maze that you saw. Now that gets loaded up in a map as, okay, point 0, 0 has a color of 1, okay, where 1 is blue and red is 256. And if the color next to it is red, then you can traverse in it. And if the color next to it is blue, it's an obstacle. And you never ever, again, the rule of Dijkstra is you have to investigate each and every node. So you will have to investigate the obstacle as well. So that's why in this you will see that you always end up first checking if you are in red or you're in blue. Because if you're in blue, you need not investigate. You can never go through obstacles, right? So that's the whole idea. And from there on, we end up getting the list of successors. What that means is we find in negative x, negative y, in the negative x, negative y, positive x, and positive y direction, is it traversable? If it's traversable, we add it to a set of successors, which we'll end up investigating in the next step. I want to take a pause here. Does anybody have any questions? No? Okay.
Can you remind again, what are your constraints in terms of memory for this device?
Okay, so the question for the video, I'm going to just repeat the question. The question was, what are the constraints in terms of memory? So the EV3 brick has 64 MB of RAM, and when I load up the JVM, that takes up about 12 MB. And this whole graph is comprised of 14,000 plus points, and constructing the adjacency matrix and all of those things. I also, the third-party libraries, et cetera, I'm left with round about 2 megs of memory, which I can use as a buffer. Okay, any other questions? No.
Nikhil, maybe you could talk about what happens when you run it with the JDK collections versus Eclipse collections.
Yeah. I will.
Oh, you're going to cover that later.
Yeah. And then for Dijkstra, you want to minimize the cost that it takes. So for you to minimize anything, you first need to know something, right? And you end up finding out the cost by a simple function. And the whole idea is it's x cost plus y cost, but the next step is, move this slide. So this step is where you actually want to prioritize which nodes you want to visit first. Because once you have gotten the cost, you actually want to know, should I be investigating this first, or is there another path which I can investigate first and find out, all right? And we end up, since I was using Eclipse Collections, you can actually end up using the Eclipse Collections API, which has a min by on it, so you can find for the cost, because if you do a vertex cost map.get, you get the cost to visit that vertex. And you can find the minimum that it's going to take to visit any vertex by just calling a min by on it. I think we can skip this slide. Oh.
Do you want to go back to that one?
Yeah. Let's go back. Sorry. So the vertex, like at the end of it, you end up getting a big map with the cost that it takes to visit each vertex from the vertex where it was before. And this is going to be the most important map that the whole software, that the whole program constructs. And why is it important? Because when you're starting at point A and then you're going till point B, all right, that time when you're trying to visit each and every one of the points in between, you have to make sure to find out where did I come from, okay? And in order to get to where did I come from, you always need to come from the point where it was the least to get there. Okay, sorry, that was a bit convoluted, I understand. But it becomes an interesting problem to figure out where, okay, if you have 3 points, or let's assume you have 4 points, you have, when you're going from point 1 to point 2, it costs 1 unit. If you're going from point 1 to point 3, it costs 2 units. And if you're going from point 1 to point 4, let's say it costs 3 units, right? Now, you know, and later on in the whole graph, everything ends up, mapping, and all of these 3 points actually join to the ending point, which is point B, right? Right now, your least cost path is going to be point 1 to point 2 to B, okay? Assuming that from those points to the end point is the same cost. But you need to know that that's the least cost. That node 2 was the node from which you have to travel. And for that, you have to create a back pointer map. I call it a back pointer map because that map tells you from where you have arrived and where you need to go to, okay? And we end up using that to actually find out the whole path. Again, I'm giving another shout out to Eclipse Collections because we are using the Eclipse Collections stack where it is last in, first out, instead of first in, first out like it is for the JDK stack. And this behavior becomes important because now what you can actually do is you start at the start of your you start at the starting point of your maze, and then you keep on seeing, okay, where do I need to be, where do I need to be, where do I need to be, if I was using a JDK stack or a list. But now it's easier to always go from the end. How many of us have always solved a maze? At least I used to solve the maze by going from the end to the start, because that's quicker to solve. So now that you have solved everything, you know what is your endpoint, you can pick up your endpoint and you can see, okay, in order for me to get to the endpoint, I need to go to n minus 1, n minus 2. And in the previous slide, we already constructed the backpointer map. And with this stack implementation that Eclipse Collections has, you will end up putting all of them on a stack. And now you have this nice list, or now you have a nice stack of actually vertices which will help you travel from the starting point to the end point. Yeah, go ahead.
How does this correspond to the physical world? Like, what are this is exploring the maze as it's doing this?
No, it cannot.
The maze loaded into
Yeah, so I'm going to repeat the question. How does it translate to the physical world? Does the robot first explore the maze, or the maze is already loaded on the robot? So Dijkstra is a knowledge-based algorithm. What that means is the whole maze has to be loaded on the robot first. If it has to explore the maze and then figure out the path, then we are working with a different type of algorithm, like a SLAM algorithm, where as and how it is traveling, it goes on figuring out, hey, can I travel here, can I not travel here? And at that time, that's basically you'll first go do an investigative run, and then you'll figure out what was the least cost. Versus a knowledge-based algorithm means you already have all the information beforehand. Okay. So this is the path that it generates. As I had mentioned before, it has two options, going to the right or going to the left. It chooses to go to right because it's cheaper. And previously I mentioned A star, so I wanted to show A star as well. And you can see it's the exact same path, okay? But if you look at the heuristic up there, the heuristic is x of endpoint minus x of point 2. Again, consider like heuristic is an art. So I just wanted to put these slides out to show how a small change of a heuristic actually can change the path. Because in the next slide, you will see that instead of y.2, I actually have x.2. And that causes the whole shift. Because if you'll see, what I'm saying is I'm trying to minimize my heuristic as well, right? So out here, it's trying to favor going more in the y direction than in the x direction. Again, at the end of the day, it has to travel that much, but it just depends which side it will favor more. Okay, any questions? No. Okay, next one. So going to the last part of the presentation, and then we'll move off to demos. And if you want to chat, we can chat after the session. So the whole path was comprised of 226 nodes. And again, those nodes are considered like, consider them to be just pixels. So basically, there were 226 pixels through which the robot had to move. Now, when you're trying to move through 226 nodes, you're going to stop 225 times, right? Because you go there, then you figure out, oh, I need to go to the next point. I need to go to the next point. I need to go to the next point. So you need to make sure that how will you achieve this motion without pausing 225 times? We just flatten the path. And when I say flatten, what I mean is you try to have, again, going back to the concept of Dijkstra being a knowledge-based algorithm, once you have the whole graph in memory, you can get the path in memory. Now that you have the path in memory, you can actually keep on seeing if the next point is traversable or not. And not only that, you can also see if the next point is in the same heading or not. And when I say in the same heading, what that means is if it needs to keep on going straight, it needn't stop there. It actually need not even travel till there. Okay? If it needs to turn left, then it can just go there and turn left. So for that, we don't only look at the next point, but we look at the next to the next point. All right? And what that means is, hey, if let's say I'm going from point A to B to C, if A and B are in the same heading and B and C are in the same heading, you can just go from A to C. Okay, if you're going from A to B to C, but C is a different heading, I need to know while I'm at A that, hey, I have to go till B, stop, and then turn. Does that make sense? Yeah.
Just one question. You mentioned that if you only go check 3 points in advance, why can't you just check whatever, as many points as you want to, if there's a contiguous block?
So the question was, why do I only check 3 points in advance? Why not all the points in advance? I do check all the points in advance. I mentioned 3 because 3 are the minimum that you need to check. Maximum, so if the third point is also in the same heading, just keep on pushing it on the stack. Okay, I'm going to skip performance, but go directly to the interactive demo. We have demos on for the robots where you can actually control them via Twitter, and Luke will explain while I pull up the program and start it up.
So what we have here are 2 of these Mindstorms set up as shooters. So as you can see in here, they have a small rack of small ball that they're going to shoot. We've got a bowl in the middle. This is because we couldn't find a gong. And what we're going to ask you guys to do is tweet with these hashtags. Nikhil is going to spin up a small application on his laptop. It's going to poll the Twitter APIs every 15 seconds for tweets with these hashtags and the directions. So this is Nikhil just doing a quick test. It missed the gong. There we are. So as you can see, that was a very quick test run. But I'll let you all to start tweeting, and we'll see what chaos ensues. So the way it's going to work is if a few of you tweet forwards and a few of you tweet backwards, it might just move forward and backwards. It's going to choose the top occurrences of the instructions it received. So if everybody asks it to sound the gong, it will sound the gong. If everybody asks it to move left, it will move left. So I'm also going to start tweeting now. So I think one of them is labeled Nikhil EV3 and one of them is labeled Luke EV3. So if you can just go tag that. And of course, please tag DevOps US in there as well.
Yeah, we were really creative with our names. Also, the interesting thing about actually using the Twitter API is like, and again, we did that at Java 1 as well, and it's slightly a different problem to solve because let's say you have like 5 people tweeting 5 different things. It's going to be chaotic, and you don't know how the robots are going to behave. And you cannot keep on like making it do stuff over and over again.
Look out, it's going to aim at you now. Yes, please refrain from aiming the shooters at the audience, please.
It's an audience's control whether they
Yes, yes.
Someone want to keep on making it turn right or left? I can.
I think
This is Nikhil. That is
this one's Luke.
Luke seems to be more abiding of the
Oh, look out, Don. There we go, again some action now. Yes, it does keep doing that.
Don't shoot.
So I'm going to aim at our favorite Don lab right here. Is it going to shoot as well?
It depends.
It is up to you guys. If you don't tweet, nothing happens. Twitter tells you you've already sent a tweet.
Okay, we are trying to aim there. Oh! sturdy.
Yeah.
They have been through my TSA check and that.
Obviously, we can leave you. Oh, is mic back on? Yeah. Obviously, we can leave you to keep playing with that if you wish. But I think we're also free to answer any questions you might have about it as well. And thank you for coming.
Please rate our talk, even if it was good, bad.
So
I hope it wasn't ugly.
Can you say more about the memory usage?
Yeah. So
Special collections. I don't know, going way back when I tried Lectures, one constraint was that it would never free memory. So you
Yes.
had to write your program such that you use memory and then you reuse array elements. You
Yeah.
couldn't just call new.
yes. I'm just going to repeat that for the video. So the question was about memory utilization. A gentleman out here had an issue long back when they were using Lehurst that the memory wasn't cleared. So I did observe that. So my very first implementation used JDK and normal hash maps, hash sets, all the JCF collections which are available. What used to happen is the whole algorithm will be solved, and after that the robot would just die because the memory was not getting garbage collected. The objects were not getting garbage collected. But when the reason why I moved to Eclipse Collections was I ended up having that 2 megs of memory buffer. I think it was sufficient enough for the program to keep on running over and over again. And if you see in the implementation, I'll end up pushing it to GitHub. If you see in the implementation, I'm actually not creating new objects. I keep on reusing the exact same objects. So with that sort of implementation, since the memory, the references should get reused, and I'm not creating. Oh!
Yeah.
Someone really hates our robot. They're making them fall over and over again. Okay, but sorry, to go back to the go back to the answer, I went through about 15 iterations so that I can keep on solving the Dijkstra's algorithm at least 5 times without having to restart the robot. And with JDK, it would do 1 or a couple of times, and then after that, it would just freeze. So it was a broken GC. I think that problem still exists, which you mentioned. Yes.
And the talk also mentioned that you guys play with Raspberry Pi for this project.
Yeah, so I tried to get the Raspberry Pi working such that, and I was talking to Steve Chin, who, according to me, is a Raspberry Pi expert, where instead of me spinning up a server on my laptop, it could spin it up on a Pi, and then I need not have all the cables dangling around to my laptop. But I was unsuccessful in that, and I will keep on working at it more, and I'll be speaking on the same topic at GIDS, Great Indian Developer Summit. Hopefully by then, I should have it working. Any other questions? Because this was the end of the talk. I'm happy to talk about robots for rest of the day.
How do you use it in Goldman, if it's not a secret?
The interesting thing about working in Goldman is
You should stay behind the mic.
Sorry, old habits. The question was how does it connect with me working at Goldman Sachs? So if you look at any problem, it's not that different than any problem that we solve at Goldman. We end up writing code which satisfies our business requirements, and the code is complicated. All right, and again, going back to why Eclipse Collections was even made, because before Eclipse Collections was migrated to the Eclipse Foundation, it was called GS Collections, which got open sourced in 2012. And before that, it was called Caramel internally. And the development actually started from 2004. And along with that, we open sourced another framework last year. It is called as Rela Domo. It's our own domain-specific language, where it's an ORM. I won't say it's a DSL. It's an ORM, and it's different than JP, or it's different than Hibernate. Now, both of these frameworks came into existence because we had that business need. We needed to make, like, for Eclipse Collections to be born, we were dealing with 100 GB JVMs back in 2004, and the creator of Eclipse Collections is actually in the audience, so you guys can talk to him afterwards. As well as we are giving a talk tomorrow on Collections Compare, where we are going to compare different collection frameworks. And there you will see how we end up using the memory constraints, like how we are playing with the boundaries of the existing ecosystem. Going back to how does it, conform with the work at Goldman Sachs, it was a problem which I found while I was playing around, and there was a creative way to solve it, and I solved it. That's what exactly we do at Goldman Sachs, but instead of solving it on a 64 MB JVM, we solve it at a higher memory JVM. And the problem out here was downscaling. Out there, you're writing bespoke code for business applications, and up there you'll be upscaling. So does that answer your question? Okay. Any other questions? All right, thank you very much for spending this morning with us, and I hope we did a good job. Please rate our talk, and have a good DevOps US.